The last lecture is on design of experiments. We call it DOE in short. Design of experiments is a concept that was devised by Professor Ronald Fisher in 1920. Then few decades it was not even talked about, though mechanical engineers itself did not talk about it much. But when the resources to do a complete census inspection, resources to have samples in hand, and then doing experiments, while doing experiments itself, some of the experiments were not even required to be done, and small number of experiments would give the same kind of the output with a very significance level of maybe 6 sigma. It will give the results whatever would have been done with maybe 1,000 experiments could be done in maybe 20 experiments, 30 experiments. So this was done through design of experiments. There are methods of design of experiments which I am not covering in this course, but I will give you brief introduction what are the various terms of the design of experiments. There are methods such as response surface methodology, factorial design, Taguchi design of experiments, multiple ways to reduce the number of experiments to be conducted, and the kind of a similar kind of the scenario analysis. So what we will walk through in this lecture is an introduction to design of experiments, terminology used in it, steps and correlation and regression, and how do we need to understand regression to have our hypothesis or our experimental design ready. Design of experiments. The purpose of statistically designed experiments is to collect appropriate data and to analyze it with statistical method, resulting in valid and objective conclusions. Two aspects of the experimental problem are the design of experiments and statistical analysis. We talked about statistical analysis. Once an experiment is designed, statistical analysis has to be conducted. That is a hypothesis testing. Whatever we have discussed in the previous lecture is taken into account. Design of experiments is important. Once we define the problem, determine the objectives, determine the responses and factors, design experiments is then done so that we conduct experiments in the minimum possible time with the minimum expense of the resources. Then we analyze the data, interpret the results, verify predicted results, and also some additional experiments for validation, those are required, are taken. So what is specifically design of experiments? I will give you. I would like to explain the design of experiments concept with help of this example. You see, in machining, for instance, you have to have a roughness of specific level. For that roughness, in machining, there are certain parameters which are selected. For example, cutting speed, that is the spindle rotation, the depth of cut, the feed, the kind of a tool that you use. This all becomes the parameters which are to be finalized or optimized so as you have the final roughness as desired upon your application where you are going to apply that specific component to be manufactured to. Now, let me take an example of baking a cake. For baking a cake, we have certain parameters. For example, we have temperature of oven, we have sugar, we have flour, we have eggs. These are the resources available. And for instance, if you have 3 levels of each, the temperature for example varies from 150 degrees to 250 degrees, and center point could be 200 degrees. I am talking about degree centigrades. Then sugar could be 1 cup, 2 cups, 3 cups. Flour could be, I would put 2 cups, 4 cups, 6 cups. Egg could be 1 egg, 2 egg, 3 eggs. So these 3, 1, 2, 3, here also 1, 2, 3, total 3 each becomes levels. I will talk about the terminology. Total number of experiments to have a perfect combination or perfect result of what should be the right combination between the oven temperature, the sugar, that is the amount of sugar, the flour and eggs, we would have to conduct 3 into 3 into 3 into 3 is equal to 81 experiments. Conducting 81 experiments and maybe spoiling some of the cakes because of the extreme which are not even required, this is not a great idea. That is why design of experiments is required. Here what are we doing? We are trying to adjust temperature maybe at one specific level. For example, let me say parameter O, S, F, E, and each of them are having levels 1, 2, 3. I will say O1, S1, F2 and E2. What does this mean? O1 is set at 150 degrees centigrades. This is 1 cup of sugar. This is F2, flour 2 means 4 cups of flour. This 2 is 4 for the flour. And E2 means 2 eggs. This one specific set that we are working upon is known as one treatment. Like this I talked about, we would have to do 81 treatments, and out of these 81 treatments, after baking the cake, what do you need to identify? We would have response parameters here. Response I will call as variables, which is taste, color and consistency. The taste of the cake, with more sugar it will be more tanginess, with higher temperature the color would become more dark. The consistency would be depending upon maybe egg or some other factors. So, we do not know which of these, when I say factors, I am talking about the input variables for which different levels are there. In case of baking 81 cakes, in place of 81 experiments, there could be half factorial in which half of the experiment would be conducted, and in factorial analysis or in response surface methodology, generally the extremities are always taken. For example, 1 level of all the 4 factors here, and 3 level of all the 4 factors here, and middle level is also taken. Then combination between 1, 2, 1, 3 something, these are decided upon kind of the design of experiments we are trying to working upon. So, this is we would have conducted with 4 variables. There is methodology as I talked about RSM, 4 factor, it would suggest 30 experiments max. In these 30 experiments also we have 6 replicates. Why do I say replicates? Because if one time you have taken the best cake combination, for example, at specifically maybe level 1, 2, 3, 1, you have gotten a specific combination that is best or most acceptable cake that you will finally put to the customer with the best taste, best color and best consistency. That is only one time you have done. Replication, this experiment would have to be repeated at least 3 times to see whether the results are replicable or not. Here out of 36 are replicates. If I remove the replicates, 25 experiments are an F in place of 81. Now, for instance, you would have 5 levels, 100 degrees, 150 degrees, 200 degrees and 300 degrees. Then where we will have 1, 2, 3, 4 and 5 cups of sugar, 2, 4, 6, 8 and 10 cups of the flour, 1, 2, 3, 4 and 5 eggs. Here what will be the total number of experiments? That would be 5 into 5 into 5 into 5 is equal to 625 experiments. Very large number of experiments, but still RSM will suggest you only 30 experiments. So, this is the magic of design of experiments. You understand all the extremities, then you try to see what is the center point and how do you see the variation in between, that you can have experiments in between designed. Now, what do we have here? In any kind of a setup, this is baking of a cake. It could have been selecting the parameters for running a turbine. For running a turbine, there are 4 parameters selected, for example. 4 parameters have each of their settings, and each of the settings are designed at what is a specific setting at which the turbine would have maximum efficiency. Or maybe we will say where in the turbine blades there should be minimum 2-3 responses which can select. In the case of the machining itself, the response parameters could be quality and also the performance. Performance in a way, quality would be the surface roughness what we are getting. The performance would be what is the tool wear. Tool wear is to be minimized, surface roughness is to be put to a specific level. So, the way we design it depends. Those are all output parameters y1, y2 till ym varying from yj. These are the output parameters which we are working upon. So, we aim or design of experiments aim to correlate these outputs y1, y2 and ym, whatever we are talking about, whether taste, consistency or color, whether surface roughness, tool wear, the cutting fluid wastage, based upon the input parameters that could be speed, feed, depth of cut, kind of the cutting fluid you are used, kind of the tool material you are used, kind of the material tool combination you are used. This all happens in the presence of the uncontrolled variables. When I say uncontrolled variables, in presence of uncontrolled variables, which is Z1, Z2 and so on up to Zc, this is also known as noise variables. For example, in this cake, I took only 4 factors: oven, sugar, flour, eggs. What about additives? What about the quality of sugar? Are we using really fine grained sugar or we are getting sugar from a different kind of a store? What about the kind of the egg you are using? What about other parameters? The way you are mixing, the time you mix for it. So, these are all parameters which you are fixing, which you are not even varying. Only the parameters which are most significant we are trying to take into account. Other parameters could also be there, which are known as uncontrolled variables, because in machining itself the uncontrolled variables are there when we are doing the experiments. Though the machine should be perfect, there could be machine which is having maybe 20-25 years machine has been used. What about the machine performance? What about the human who is working on the machine? Those are known uncontrolled variables. So, this is how design of experiment is to be conducted and we try to have the overall output. Now, let me try to talk about the terms used in design of experiment. Factor, this is a variable or attribute which influences or is suspected to influence the characteristic being investigated. All input variables affect the output of a system are factors. They can be qualitative, that is type of material, type of tool, or quantitative, that is temperature, pressure, etc. We have talked about quantitative and qualitative. Quantitative is metric, again to recall, and this is non-metric. Levels of a factor, levels I talked about, up to 3 levels I worked for, 3 eggs, up to 5 levels I worked for. Levels of a factor, the values of a factor variable being examined in an experiment. If a factor is an attribute, each of its state is a level. For example, setting of a switch on and off are 2 levels of a factor of switch setting. If the factor is a variable, the range is divided into required number of levels. The levels can be fixed or random. It could be fixed or random. If, for instance, the temperature, I took only 100, 150, 200, 250 and 300, 5 levels I took. So, I fixed the specific range. It could have been 201 degree, 202 degrees, but I fixed it a specific level. What is happening between 150 and 100 would be given by the curve plot that we get through. Then comes treatment. Treatment, as I said, is one set of levels of all factors employed in a given experimental trial. For example, an experiment conducted using temperature T1, pressure P1 would constitute one treatment. What I said here was, this is one treatment. Oven at specific level 1, sugar 1 level, flour level 2, eggs level 2. This is one treatment. In case of single factor experiment, each level of factor is a treatment. Response, the result or output obtained from a trial of an experiment. This is also called dependent variable. These factors are also known as independent variables. Examples are yield, tensile strength, surface finish, number of defects, etc. Then comes effect. Effect of a factor is the change in the response due to change in the level of factor. This effect is generally presented through a regression model. Experimental error. It is the variation in response When the same experiment is repeated, I talk about replication. Replication, within what range the replication is happening. For example, if I measure the roughness, each time the roughness is coming 2.5 micrometers, but it varies between 2.51 and 2.53 micrometers. That is the only upper level of tolerance is only common. Taking percentage of 0.02 by 2.5, maybe I could say within 1% of control it is happening. So, this error is estimated as the residual variation after the effects have been removed. Designing of experiment requires attention to 4 potential traps that can create experimental difficulties. In addition to experimental error, other sources of error, that is unexplained variation, can confuse the results. Unexplained variation, the person who is conducting the experiments is not serious. The responses are not being observed through a good instrument. Unexplained variance could also be there. Uncontrollable factors that include variation under normal operating conditions, referred to as noise factors, these I just mentioned about. Correlation can often be confused with causation. Correlation only gives this is going up and down. Cause is never there in correlation. Correlation is only talking about this is happening when other is happening, this is increasing or decreasing. We will talk about correlation. Causation is a different scenario. Two factors varying together may be highly correlated while one doesn't cause the other, that they may both be having been caused by a third factor we do not know. This is to be measured. Combined effects between factors require careful planning prior to conducting the experiment. When I say combined effect, in case of if you vary two variables, for example, number of eggs and number of cups of sugar, you increase simultaneously. There would be a combined effect of both of them. This we do not know what has enhanced or reduced the level of consistency in the cake that you bake. Or if you have increased the feed and decreased the speed together, what has contribution to the change in roughness we do not know. For that, again, number of experiments are to be conducted and these are to be very carefully planned, and this all is based upon the previous experience and the secondary data which people have given where they have conducted similar experiments. Accordingly, always there has to be a starting point. The starting point is taken through one factor at a time, keeping everything else constant. Then we see what is the range of the factors that we will try to work upon for experimentation. Now, this is a more detailed version of the illustration which I showed you. I only showed you factors and levels in the previous part. Factors are also known as variables or inputs. Levels are the limit settings or measures. And I showed you responses, that is the outcomes. Outcome would come in these kinds of the graphs. This kind of the graph that you see is a response surface. In between, we have the experimental plan, that is the design matrix, randomization, test sequence, which test will be conducted first or later. Then doing experiments, actually for experiments we need to have all the tools ready with us. It is invariable test conditions. The person who is conducting the experiments, the machine should stay consistent. If you are using one oven, for example, for one make oven we are using Murphy Richards oven, let us keep doing it in Murphy Richards only. We should not move to Philip for the another set of experiments within the same set of the decision that you are trying to make. So that means there should be consistency. Steps in experiment process. The experimental objective is first planned properly to collect data in order to apply statistical methods to obtain valid and objective conclusions. The following 7 steps procedure may be followed. Define the problem statement, select factors, levels, ranges of these factors. This is done by OFAT. I am giving you terms. You can refer to the books given in the reference slide here to read more about them. This is one factor at a time. Selection of response variables. What response variables are more required to be studied? Choice of experimental design, whether we are using RSM versus factorial versus Taguchi method versus others. What is the kind of experimental design that you are trying to have here? Conducting the experiments, then analysis of data, conclusions and recommendations. In experimentation, improving the process or product robustness is most important. Robust design, it is an engineering approach to create products and processes that consistently perform well despite variations in manufacturing, usage or environmental conditions. The system should be insensitive to the noise factors, that is uncontrollable variations, or factors that cause minimal impact, leading to improved reliability and reduces costs associated with rework and defects. Balancing trade-offs. Trade-off is between one thing or other thing, that is decision making process considering advantages and disadvantages of different options, often involving give up something desirable to gain something else, trade off one thing for another. Always there would be a trade off. You might find the cake that is best with one set of the setting. There could be another set of the setting where you also find the cake that is also very great. But now, which one of them is using minimum resources? If the oven temperature is higher, the energy consumption is higher. If number of eggs are more, the cost would also go high. Then there has to be right selection of the optimal results which are there, so as you have that with the minimum use of resources, number one. Number two, there could be trade-off. With the same cost, with the same energy, you have two sets. With in one, number of eggs are 2, in one, number of the cups of sugar are little more, maybe 1 cup more than the previous one. 2 sets are completely ready. Then either you use more number of cups or either you use more number of eggs. There could be trade-off. One could have been given off than another. Or in another way, I would like to, I am talking about now only factors or variables, input variables. In the response variables, the trade-offs are more important to be decided upon. Maybe for example, amongst the consistency and color. When the taste is all equal, what would you select? Consistency or color? People sometimes look at the cake, purchase the cake because of the color itself. When they taste them, they will like consistency more. So one thing have to be completely washed away. For example, you completely wash away, I do not now prefer color, consistency has to be there. Maybe in case of tool wear, basic roughness, the tool wear is going little higher, but roughness is better. You say, okay, I will try to give away one thing for another, that is trade off one thing for another to gain something, I will have to lose something. This is trade off, to balance trade off. To balance trade off, one has to identify the options, evaluate pros and cons of them, and select the option that can give the best overall outcome, making a compromise to lose some option than other, which may give few much better but overall lesser outcome. So, I am not talking about these methods here, response transfer methodology, factorial method, Taguchi method or any other. This you can read. Owing to the time availability, I have given you a brief introduction that design of experiment is required, and that is one of the important or critical thing when you try to really conduct the experiments with the available or minimum resources. Now, let me talk about correlation and regression. When you conduct the design of experiments, in the steps you could see there is analysis of data. This analysis of data, as I mentioned, generally we try to have a regression model. To have a regression model, we need to understand what is correlation and what is regression. Correlation is a statistical measure to describe the extent to which two variables are related to each other. It indicates whether they tend to change together in a consistent way. This relationship can be plotted and displayed on a scatter plot and is quantified by a correlation coefficient which ranges from -1 to +1. A positive correlation means variables increase or decrease together. A negative correlation means variables move in the opposite directions. Correlation near zero indicates no linear relationship. Correlation does not imply causation. This is always there. Causation and correlation should not be confused, meaning just because two variables relate to each other does not mean one directly cause the other. So, here is a plot. When I say correlation coefficient value 1, it is a perfect positive correlation. With change in one, other thing is directly changing. For instance, by adding sugar, the sweetness would go high. So, this is positive correlation. Strong positive, which is not perfectly 1, but yes, it is also varying in a positive direction. Weak positive, it is having some scatter, but it is still positive correlation. 0. completely scatter plot and no correlation. Exactly opposite direction, this is 45-degree angles, and when we have a negative 45-degree angle, this is a -1 correlation, 0.9, 0.5, 0, no correlation. Now let me talk about regression. Regression is a method for studying the relationship between variables, particularly how a dependent variable changes in response to one or more independent variables. It aims to find patterns and trends in data, quantify the strength and direction of the relationships between variables, predict about dependent variable based on changes in independent variable. Key concepts: there is a dependent variable that I call as the response variable. This is the outcome or response variable to be predicted. There is an independent variable that I call as factors, which are input variables that are believed to influence the dependent variable. This is a regression model, that is statistical model to establish a mathematical equation, describe the relationship between x and y, often represented by a line or a curve that best fits the data points. Simple linear regression, multiple linear regression and logistic regression are 3 types. There could also be nonlinear regression as well. Simple linear regression explores the relationship between one dependent and one independent variable using a straight line. Multiple linear regression examines how a dependent variable is influenced by 2 or more independent variables simultaneously. The examples which I took, baking a cake, machining, those were all multiple linear regression examples. We are trying to identify or see how surface roughness is dependent upon the speed, the feed, the depth of cut, the type of tool. So that could be multiple linear regression. Logistic regression is something different. This is used when dependent variable is categorical. For example, yes, no, pass, fail, predicting the probability of that event occurring. Applications are in manufacturing, that is predicting machine failure, optimizing resource allocation, in business and finance, predicting sales, analyzing investment risks, in healthcare, studying the impact of lifestyle factors on health outcomes, machine learning, that is building models to make data-driven predictions. Simple linear regression is put in this way: y, that is dependent variable, is equal to beta naught plus beta 1 into x plus e. This is dependent variable, this is independent variable. Epsilon is the regression error term, that is model that we have developed is not a perfect match. There is an error, this error has to be minimum. There will be multiple models which would have come through the analysis. Whichever model has the minimum error would be more close. Multiple linear regression, when y is equal to beta naught plus first variable, second variable, third variable, so on up to tth variable plus error. All these variables have their coefficients along, that is beta 1, beta 2, beta 3, it is given here, beta 1, beta 2, beta 3, so on up to beta t are beta coefficients. It is the slope of the explanatory variables. Beta naught is the y-intercept, that is at least this value would be there. The explanatory independent variables used to predict is x, y is dependent variable. Epsilon I have also given, it is regression residual or error term. Let me see an example. Multiple linear regression for prediction of gas turbine performance. Gas turbine performance is turbine would run, it will produce electricity. Production of electricity, that is power output, is dependent upon what variables? In a combined cycle power plant, which is also known as CCPP, utilizing gas turbines and a steam turbine, both of them together, the net electrical power production, that is dependent variable, can be presented as a linear function of many independent variables, including the ambient temperature, AT in degree centigrades, exhaust vacuum in millimeter of mercury, that is pertaining to the steam turbine, ambient pressure in millibars, relative humidity, that is a dimensionless quantity. This is a multiple linear regression model for the turbine power output. Here PO denotes anticipated electrical power output, which is equal to beta naught plus beta 1 into ambient temperature, beta 2 into exhaust vacuum, beta 3 into ambient pressure and beta 4 into relative humidity plus the error term. Now here beta naught, you know what is it? Beta 1, beta 2, beta 3, beta 4 are all the coefficients for each variable indicating the change in the power output for 1 unit alteration in the respective variable. For example, if ambient temperature is raised by 1 degree raise in ambient temperature would imply beta 1 times change in power output. I am putting the word change. I did not write increase or decrease because we do not know this beta value could be plus beta 1 or minus beta 1. We do not know what value this could be. Now, utilization in turbines, there is one equation that I have taken from the University of California database where they have given this combined cycle power plant system. In utilization turbines, engineers utilize past operational data obtained from the SCADA system to compute the values of beta coefficients. The resultant model often enables them to forecast power output, that is anticipate the power generation of turbine under varying climatic conditions such as hot, humid day compared to a cold, dry day. Performance evaluation, that is establish a benchmark for anticipated optimal performance. A substantial discrepancy between the actual power production and the model's projection may indicate performance deterioration or a possible malfunction in the turbine components. Then analysis of efficiency is also helping them. Examine the coefficient to measure the influence of each variable on overall efficiency. A marked negative beta for ambient temperature corroborates established technical premise that gas turbine performance diminishes substantially with the increasing ambient temperature. So, let me show you. You see there is a negative sign here, which means by 1 unit change in the ambient temperature, 1.98 times, that is the coefficient value here, 1.98 times into 1, that is 2 units almost of the power output would decrease, which is 454.61 as the baseline predictive power output in megawatts. This is for example. Beta 1 is equal to 1.98, the power output decreases by about 1.98 megawatts for every 1 degree increase in ambient temperature. Power output decreases by 0.23 megawatt for every 1 millimeter of mercury increase in exhaust vacuum. You see word decreases are there whenever negative sign is there, and for the ambient pressure the word increases is there because this is the positive sign. Which mean it increases. Power output increases by about 0.06 megawatt for every 1 millibar increase in ambient pressure. Similarly, there is a scenario given for the relative humidity, that is it decreases by about 0.16 megawatt for every 1 unit increase in relative humidity. If relative humidity is on a 0 to 100 scale, this is per 1% point. I am not going to more details of regression models itself. There are combination factors as well. For instance, this is just a direct or main effects which have been given. For instance, if it is 454.61 minus 1.9880 and so on, these are all main effects. Main effects. There could also be an interaction effect. For example, let me say there would be some value minus 0.32 when AT, that is ambient temperature, and vacuum pressure is taken together and exhaust vacuum is taken together, AT into V. Maybe plus if suppose ambient pressure and relative humidity are taken together, this is 0.23 times ambient pressure into relative humidity. These are known as interaction effects. For this, you can read the book that I have given. There is a book by Douglas Montgomery which has given in the reference, and there are multiple other books which are given in the reference. You can read about them. If any queries, you can come up to the forum for any questions. Just to recapitulate what we discussed in this lecture, we talked about what is the purpose of design of experiments. We saw the terminology, factors, level, treatment, what are factors and level in DOE. This is one of the questions. What are the key steps in design of experiments? Why is randomization important in experiments? What does correlation coefficient measure and how do we interpret the positive correlation? What is regression analysis used for? Difference between simple and multiple regression. With this, I am closing my talk and lecture series on the design of experiments and also on statistics in mechanical engineering. With this, I am also closing the basics of mechanical engineering 3 course, which is a 12-week course, and we discussed about thermodynamics and fluid mechanics. This also closes the overall series of the basics of mechanical engineering by Professor Ram Kumar and Dr. Ramandeep Singh, that is I. And we hope with the virtual demonstration, with the tutorial sessions and with the theory, you might have learned. If any queries, we are open for any input and feedback that you will provide us. Thank you.